on unlikely intersections in elliptic surfaces and problems of mass.
Thank you very much. So in the last lecture, I have discussed unlikely intersections in the multiplicative group context, and today I shall turn to the context of abelian varieties. As I mentioned, here there are many results and conjectures completely similar to the multiplicative case, and sometimes less complete because of the lack of tools like height estimates and similar. And for instance, the Zilber conjecture that I stated for multiplicative groups admits a completely similar analog stated by Zilber himself in the case of abelian varieties. So let me, however, go back to the original length question of torsion points on a curve, on a plane curve in the square of multiplicative group. And this has, may be seen as an analog, is the Manning-Mumford conjecture, proved eventually by Renault, which predicted finiteness for the torsion points in a curve of genus at least 2 embedded in its Jacobian over a field of 0 characteristic. And this conjecture was proved by Renault actually in a more general form, which I restate. Theorem I think it is dated. So let A be an abelian variety over a field of characteristic 0, and let sigma be any set of torsion points in A. Then the Zariski closure of sigma is a finite union of translates of abelian subvarieties of A by torsion points. So this is completely analogous to what I had stated for multiplicative groups. And there are several proofs came after the Renault's original one. To my knowledge, none of them is really easy. They lie in a deeper level than the corresponding statement for multiplicative theory. And a recent proof was given in a joint work with Pila with a method that of which I outlined the essentials in my first lecture. And this is the method which I would like to discuss today in slightly more detail. But actually, I shall not deal directly with this statement, but with the same method applied in the context, applied to the solution of certain problems of Masser, which may be seen as Manning-Mumford for a variable abelian variety. And actually, I shall deal only with a special case of an elliptic surface. So, and in the course of this discussion, I shall also recall how to apply this method for the original theorem of Renault. So let me recall the Legendre elliptic curve, which I denote by E lambda, and defined by this equation. And we may view we may view lambda as a variable, and in this case, this elliptic curve may be seen as an elliptic curve over the field Q of lambda, for instance. Or we may also think of specializing lambda to, for instance, complex numbers different from 0 and 1, and we obtain a surface, which I call, for instance, A. So I call the surface corresponding to this, and I view it as a surface with a map denoted again by lambda over C minus these 2 points. So let us now take 2 points, P lambda and Q lambda, and we take 2 points defined, for instance, on this curve, and defined over the algebraic closure of this ground field. And for simplicity, I shall make the Masser's original choice in stating the problem. Namely, he chose P lambda 1 point with abscissa 2, so the first integer abscissa which is legitimate. And Q lambda, this one with abscissa 3. So, and these points may be seen also as giving curves on the surface A. And we now can think of specializing lambda and specializing the points. And Masser's question was what can be said about the complex, let us call them lambda naught, not 0 of 1, such that both P lambda naught and Q lambda naught are torsion. This was the original question. We note at once that none of the points is identically torsion. And this can be seen, for instance, by observing that the field of definition is ramified over points different from 0, 1, and infinity, and so this is one proof, or also by specialization. So, so let us discuss a little bit this question. So, and first, let us take a single point. Let us take a single point and ask when, for instance, we take P lambda and ask for the values which make it torsion. So if we compute the multiples of P lambda, we obtain an abscissas which are given by, here there will be a corresponding function. And these AM, Bn are polynomials, coprime polynomials, with rational coefficients. And the values of lambda which make P lambda torsion are the roots of Bn different from 0 and 1. And these Bn's have degrees which seem not so easy to calculate exactly, because there are cancellations if one carries the generic point, the multiplication, the generic point, and then one specializes. Anyway, one can say a lot of these degrees and also calculate a few ones of these. For instance, B2 is lambda minus 2, B3 is lambda square and so on. Anyway, one, of course, would expect that there are infinitely many values for varying n, infinitely many values which make a single point torsion. And this is in fact so. It is slightly less obvious than one could expect because Bn a priori could be a polynomial or could be made only of factors or roots from a finite set. But in fact this cannot be so because of for instance, of Siegel's theorem over the function field Q of lambda. If Bn would be made of only of finitely many factors, we would have an infinity of S integral points on that curve. But there are also other methods to see this. So for a single point, there are in fact an infinity of suitable values. And these values, so there are infinitely many values which make P lambda a torsion. However, these values are sparse. And this follows from estimates, all the estimates of Masser. But it also follows in a sharper form that we shall also use later from a theorem of Silverman, which admits a very easy self-contained proof in this special case. Theorem of Silverman implies that since P lambda is not identically torsion, so the lambdas which make it torsion, of course they are algebraic numbers because these polynomials are with rational coefficients, but actually they are algebraic and have bounded height. So there is sparseness, and similarly, of course, for Q. So requiring the condition for both, of course, we have double sparseness, and we may expect finiteness. And this was what, in fact, Masser expected, and we eventually proved. And this, to put the thing in the context of unlikely intersections, as I described it in the first lecture, we may also notice that we may form the product over P1, so considering this map, the square of the surface A, and then we obtain this is a threefold. Yes?
You're saying that the lambdas for which this P lambda is chosen are all of bounded height?
There is a bound for the height, yes. The degree, of course, this will force the degree. Since we know that there are infinitely many of them, the degree tends to infinity.
So why does this force them to be sparse? In what sense?
Well, a set of algebraic numbers of bounded height is sparse. If I take lambda with height larger than this bound, which is easy, I will get surely a non-torsion value. I mean, for instance, there are only finitely many such lambdas of bounded degree. So this is you may describe it as sparse. Okay, but we may see also in this way, this is a threefold, and the point, if we view this point here for varying lambda, this describes a curve, and imposing, if I choose two integers, m and n, and I impose these conditions, that both mp lambda and nq lambda are the origin, again, this describes a curve. So we have an unlikely intersection when it happens that this holds. And in the spirit of the previous lectures, we may expect that even letting the curve vary, it has only innumerably many possibilities, and so also the union of these unlikely intersections will be finite. Of course, I noticed that here it is essential so there are other choices of the points, of course, which would make this a false statement. And beyond the case in which one of the points is identically torsion, there are the cases when the points satisfy identically such a linear relation. And this amounts to this curve to be contained in a subscheme, in a group subscheme of this product. So these are the special varieties for the problem in question. And that this is not so for our choice is again very easy to see, because the points are defined over different quadratic fields. So if this relation would hold, then by conjugating in the possible ways, we would see that this would change the sign as we wish, and so the points would be identically torsion, which we have already excluded. So this, in our case, this is not verified, and indeed, so we may they do not lie in a spatial curve. So let me say also that here we see a case of a conjecture of Pink. Pink made a conjecture in a paper which is still unpublished, I believe. Anyway, of which this one is a special case. For brevity, I will not repeat it, but it is phrased with group subschemes, abelian group subschemes, and
I heard about this paper, but I'm not seeing it either.
yeah, it's I think he doesn't want to publish it. It is on in his web page, yes. So let me now describe the proof of finiteness very briefly. So let me recall now the proof obtained with Pila that we gave for the statement of Renault, the essentials of the proof. So we have the abelian variety. Sorry for the clash, that here A is the surface, but now I denote the abelian variety. So the steps of the proof were these ones. We began to choose an analytic isomorphism of the abelian variety A with a complex torus. And the point is now to take an arbitrary algebraic subvariety of A and prove that if the torsion points are Zariski dense there, then this X must be a translate of an abelian subvariety. So we consider the inverse image X tilde in this complex torus, and we note that by choosing a basis of lambda, we may view the torsion points on A are those with rational coordinates in the basis. So with respect to these real coordinates, we view this X tilde as a real analytic subvariety. And we want to say something on the rational points on this X tilde. And here is the first ingredient, which comes. First ingredient is to estimate the number of rational points on X tilde. And this comes from a paper, the first paper in this direction was by Bombieri and Pila. They estimated the number of rational and integral points on algebraic curves, and it was the first paper to do this in a uniform way. So where the coefficients of the curve did not enter into the estimates, but only the degree. And simultaneously with this, they also estimated the number of rational points on the graphs of transcendental graphs. And which is the direction which is relevant for this application, because here the x tilde will be transcendental, not of dimension 1, even if x is a curve, of course. Let us take the case of a curve, which was the original Manning-Mumford conjecture. This will have a real dimension 2, of course. And so a generalization of these estimates is needed. And this was carried out by Pila for surfaces, and subsequently by Pila-Wilkie. So this was for curves, and by Pila-Wilkie in general.
The number of points of height less than.
Yes, I stay. Yes, the theorem is. The theorem applies to subanalytic. This was a suggestion of Bombieri to consider subanalytic objects. And in a compact region. So we take a compact subset. And we want to estimate the number of rational points on this compact subset of the denominator, number of rational points of the denominator, say at most capital N. Now it turns out that even if the surface is transcendental, to obtain an estimate suitable for us, we shall need an exponent epsilon, arbitrarily small exponent. But even if the surface is transcendental, this may not actually be true, an estimate with the exponent epsilon. We have first to remove from the surface the semi-analytic, the semi-algebraic arcs. So we denote by x tilde t, the transcendental part, we denote the complement x tilde minus the union of semi-algebraic subsets of connected semi-algebraic subsets of positive dimension. Because on this, on a semi-algebraic arc, there may be more points than we expect. So with this, if we count the number of points in x tilde t, it turns out that the number of rational points in this intersected with the compact subset, let us call it B, and having the denominator at most n, this set is bounded by a constant depending on x and the epsilon times n to the epsilon. And this holds for every epsilon greater than naught. So this was the main ingredient. So one of the two main ingredients in proving the theorem of Renault by this method. So we have this estimate for this transcendental part of x tilde. Now it turns out, for instance, if x is a curve, one must prove it, but it is true that if it contains some semi-algebraic arc of positive dimension, then the curve must be actually a translate of an elliptic curve. Because x tilde turns out to be algebraic itself, and it can be proved. It is not completely short, but it is true. Anyway, one proves this, and then the transcendental part is all of x tilde. So this estimate holds for the total number of rational points contained in x tilde in the compact part that we are interested in. So on the one hand, we have this bound. Now let us take a torsion point P, torsion point on x of order exactly n, say. Then we can conjugate, we may conjugate and form the conjugates P sigma over a field of definition. Let us work over the algebraic numbers. Over the field of definition, a field of definition for x, and this for x and a, and this P sigma will continue to be a torsion point of x of the same order. So we have at least as many points as there are different conjugates of P. So which is the degree, the number is the degree of P. And the degree of P by a theorem of Masser is bounded below by a positive constant times n to some positive exponent. So C1 and delta are positive. This was a previous theorem of Masser. So we have at least that many number of conjugates, that many torsion points on x. These give rational points on x tilde with the denominator dividing n, or actually exactly n, and we compare the estimates. So this gives the leads to the proof of the Renault theorem. Yes.
The original paper of Taylor was dealing with the denominator equal to n.
Yes.
Because it was considered the dilations by factors, so that's the same thing as.
Yes. Yes. In this, for this application, this suffices.
For curves, but not.
For the application, it suffices that. But then in subsequent papers, this restriction was removed by the same method, and the same estimate was proved for points with denominator at most n. Yeah. But it was a subtle point, in fact. But for this application, anyway, since the order is exactly this, that sort of was sufficient. So let me now describe the variation of the thing in this context. We have now we have this variable elliptic curve. So we may again do this uniformization, but of course with the variable we shall have variable uniformizations. So for each lambda not 0 or 1, we have here a torus, one-dimensional, in C, I mean, and these are lattices which vary. And again, a torsion point on E lambda gives a rational point in R square once we have chosen again a basis of L lambda. And we may do this, I will write explicit formulas, choosing a basis varying analytically. And if we take the torsion point, so again we have, this gives rise to rational points. And we have various R squares, of course, which move with lambda. And we shall apply the same. So there are some variations in that. Now we conjugate a torsion point, and we obtain not, again, a torsion point on the same E lambda. We obtain a torsion point on the curve corresponding to a conjugate lambda. But nevertheless, this gives again a rational point in the surface that I'm going to introduce. And so this is a slight difference. And also, what matters here is not quite the degree of the torsion points over the curve, but rather the degree of the lambdas, because the points have degree, bounded degree over the curve as they are defined. So is the degree of lambda which is important. So to the p lambda, I had these points p lambda and q lambda. To p lambda, I associate two real coordinates, x and y, and similarly to q lambda, u and v, in which basis, well, these x, y, u, and v turn out to be real analytic. And I chose the following basis for the lattice. The lattice is z f of lambda plus z g of lambda, where we may choose these hypergeometric functions, f of lambda given by pi times the sum and the g of lambda is simply I times f of 1 minus lambda. So these are analytic, for instance, in this region. In this region here. And we now choose a much larger region. So we choose a big disk, and we remove small disks around 0, 1, 2, and 3. The 2 and 3 have to do with the choice of the abscisses for the points. And we do the following now. And we also, other function that we have the elliptic logarithms of p lambda and q lambda relative, for instance, to a Weierstrass model. They may be defined as follows. Z of lambda is twice the integral from 2 to infinity dx over and similarly we have the same integral from 3 to infinity, and these are the elliptic logarithms of p lambda and q lambda. These are also analytic in that domain, and they have a certain monodromy which can be written down easily. And now we do the following. We cover around each point in this bigger disk, we choose a path, and we can continue analytically the functions, and choose some analytic continuation in a small disk around that point. And we cover the big disk with these disks. Of course, it is not needed that the functions coincide. We chose determinations for each prescribed path. We chose some analytic continuation. So the purpose of doing this is the following. We want to deal with the lambdas in a small disk where the functions are uniform. And not all the conjugates, we shall have to conjugate the lambdas, but not all the conjugates shall lie in a given disk. However, due to the boundedness of the height, this is a second use of the, this is very essential in the proof. Since the height is bounded, we know surely a positive percentage of the conjugates will lie inside the big disk, because many conjugates, not too many conjugates can have too large absolute value. But by the same principle, not too many conjugates can go near to these small disks that we can have that we have removed. So we remain with a positive percentage of the conjugates in this domain, and then we know that still, since we can cover it with finitely many of these disks, still a positive percentage of conjugates will fall in the same disk where we have unique analytic continuations for the said functions. Good. So now we have these real analytic coordinates, and we consider the function theta of lambda constructed with all the 4 coordinates. And the image, we consider the image of this in this disk. Let us call it D. We fix a disk where we know that the many conjugates will fall. We consider the image of this, and this will be a surface, and actually a subanalytic, because it is the image of a compact disk by a function which is analytic, and actually we may shrink a bit the disk and suppose it is real analytic in a small neighborhood. So we can apply to the image theta of D the estimates of Pila. But then we have first to remove the algebraic, the semi-algebraic arcs inside this. And actually, again, there are no such semi-algebraic arcs. And the idea to prove this is simple, very simple. On a semi-algebraic arc, these functions would have transcendence degree at most 1, restricted to the semi-algebraic arc. But then, since these 4 functions are combinations of f and g with the coefficients respectively x and y and the u and v, the transcendence degree of these 4 functions on the arc would be 3 at most. But then by continuation, since the arc is supposed to be of positive dimension, by analytic continuation we would have transcendence degree 3 on the whole. And it may be proved that it is not so, for instance, using monodromy of the functions. So it may be proved they are algebraically independent. One can appeal also to results of Bertrand, which are actually much more general than this. And okay, so so we may apply the result of Pila, and the result of Pila. So let me write it here. So suppose
for the surfaces.
For the surfaces, yes, correctly. Whereas for Raynaud we need the whole. So we suppose that MP lambda and MP lambda naught, say, and the Q lambda naught are both torsions of orders m and n. And now we take the conjugates. we take the conjugates, and the theorem of Pila implies that the common order, I mean, if the common order n so if n is the common order, if the common order is n, then there are at most n to the epsilon with a constant here depending on all the setting, but not on n to the epsilon conjugates of lambda naught. So this is an upper bound for the order of lambda, or for the degree of lambda naught. And now comes the other ingredient. This is by a recent, fairly recent result of Sinou David. And this is implicit, however, in an earlier paper of Basser. We have that the maximum of m and n is bounded by a constant times the degree of lambda naught squared times 1 plus the height of lambda naught. Again, we use, it is crucial that the height is bounded. So we have that the maximum is bounded by the square of the degree, and but this is bounded by, so all of this is bounded by n to the 2 epsilon. And whereas this maximum is surely at least n to the 1/2. And so for epsilon smaller than that, we conclude that lambda naught has bounded degree, and the finiteness follows. So let me mention briefly some further.
As you noted, I think all these are effective because you get a bound.
Yes.
Once you have a degree bounded, the height.
Yes. Exactly. Yes. Thank you for the remark. Yes, it is effective. So. So some further work, well, concerns, for instance, what happens there are several questions that one may ask, for instance, replacing p lambda and q lambda by arbitrary points over the algebraic closure of q of lambda, and even over c of lambda. It turns out that all of these things can be dealt with. The complex case is cannot be dealt directly with this method, which involves heights, and it can be dealt essentially in two ways. At least we could find this, either by specialization, which involves, however, some points, some obstacles, or directly. For instance, if we think of specializing the points, taking instead of p lambda as the point with abscissa 2, let us take the point with abscissa pi, a transcendental abscissa. Then here we have the other coordinate, which is pi, pi minus 1, pi minus lambda. So now the torsion condition on lambda will give a function field over Q, which is essentially a modular function field. And because if P lambda is torsion, it becomes a modular function field. So applying some Galois theory of modular function fields, it is possible to deal with this complex case without using all these methods. And then, okay, of course, there are natural extensions to other abelian surfaces or higher dimensions, of course. These are still the object of work in progress. And for instance, 3 points. The natural analog for 3 points is again involves a difficult obstacle in that the method in principle works the same, but the ingredient of the 3 points so depending on a curve depending on 2 variables. Sorry, 3 points on this curve. Yes. Or, yeah. The curve, in fact, it may be brought into a curve depending on 1 parameter only, but then the points will continue to depend on 2 variables. So if the points depend on 2 variables, we cannot eliminate the difficulty by changing the curve. Anyway, the method in principle goes on, but the height bound of Silverman is missing, and this was recently proved by Habegger. So this is higher dimensional analog of Silverman. So, and let me also briefly mention a dynamical analog of these problems. So this came on noting that the torsion points on E lambda correspond to pre-periodic points for the lattice map. This is the map x to p expressed as a function of x of p. And explicitly, as a rational function, it is this one in the case of the Legendre curve. So if we iterate this map, and the preperiodic points are exactly the abscisses of the torsion points. So this suggests an analog, which I had asked to Matt Baker. I had asked, for instance, for other rational maps, what happens where we have not the group structure of the elliptic curve. For instance, let us iterate the map x squared plus lambda. We take, for instance, 0 and 1. And we ask for what can be said about the values of lambda such that both these points are preperiodic. So, and Baker and Laura De Marco proved the finiteness for these maps, and actually they considered all the maps x to the d plus lambda, and they proved that if a to the d is distinct from b to the d, there are only finitely many values of lambda for which both A and B are preperiodic. And their proof involves Galois equidistribution. They consider the Mandelbrot set relative both to A and B, and this set is defined, for instance, relative to A is defined as the set of lambdas such that all the iterates of A remain bounded under the map. And they prove a series of equivalences by Galois equidistribution. If both A and B are preperiodic, then for infinitely many lambdas, then the Mandelbrot sets must be equal, and then they deduce also that the d powers are equal. So this is a completely different approach. And Baker told me he thinks in work in progress he's trying to apply to other rational functions, and he does not exclude that this would cover also the case that we treated, which is not automatic because this lattice map is quite special. For instance, the preperiodic points for lattice maps are dense, being the abscissos of torsion points.
So when you say Galois equidistribution, is the statement that if you take a point of higher and higher degree, the conjugates are becoming equidistributed somehow?
Yeah. That kind of
argument in the Manin-Mumford, that of course works there, but not in the Andreault. So I think
exactly.
As far as we understand, of course, equidistribution when it works is very hard.
Yeah, exactly. But they managed to make it work for this case. Yes, it's a Galois distribution. There are various types of, because here lambda is varying, here the map is varying.
But it's of the flavor of Scuola.
Yeah, absolutely. The principles are the same, yes. Except that the map here is varying. Anyway, so, and the last couple of words, just, yes. They have only this theorem at the moment, but Baker thinks that he could extend to lattice maps and possibly much more general. Yeah, as I said, there are obstacles with these maps because the Julia set is too large, and this gives less information usually than with maps like this. Yes.
When two-dimensional systems have infinitely many common preperiodic points, equidistribution implies that the Julia sets of these two-dimensional systems coincide, or more precisely, that canonical measures. Measures coincide, but then it's difficult to deduce something from these measures to actual information.
Yeah, exactly. Nevertheless, Baker told me without any, he didn't say have proved this, but he does not exclude to proving this. Now, the situation is, because the map varies here, it's not a fixed map and you take all the preperiodic points. The situation is somewhat reversed. You have 2 points and the maps vary, so you have somewhat a slightly different kind of picture. Anyway, the last, I wanted to just to compare very briefly the methods, the structure of the methods that I have touched in the multiplicative case and in this case. So in the multiplicative case, in both cases, we had lower bounds and upper bounds. And here, the lower bounds for what? For the degrees. In the multiplicative case, this lower bound for degrees was obtained by height upper bounds, which in turn forced small height of new points, of other points. So the bounded height of certain points through the geometry of numbers for the structure is this, forced very small height for other points. And now, at this point, the small height forced large degree by theorems of Dobrovolsky type and specifically Amoroso-David. And here the techniques come from transcendence. They involve construction of auxiliary functions. And the upper bounds in the multiplicative case were simply came from Bezout. So of purely algebraic nature, and the arithmetic of the points did not play any other role. Here, for the Manin-Mumford, say, again, the lower bound came from transcendency. So theorems of Masser and David bounding below the degree of torsion points, or in this case of the lambdas. Whereas the upper bound, here is a main difference. Here come from the distribution of rational points. So here the arithmetic again plays.
That's the exact confusing thing. That's about used equidistribution. Now,
Yeah.
This is cardinality.
Yeah, cardinality. Bombiera-Pila upper bounds.
Sharp upper bounds, you say. The epsilon's the key. Sharp.
And again, this involves, I was saying, a bit of, also. Combined with transcendency technique, yeah. But we use strongly that the points are rational, even in this part. So, thank you. And thank you very much. Thank you.